I had no idea what mechanical engineering was about. But I figure it can't be that hard. Little did I know.
Oh,
I
really?
actually wanted to go to art school, fine art
Really?
school. So I had my portfolio prepared for admission requirement.
Interesting.
And I need a signature from my parents for sending in my portfolio. And they refused. So,
Really?
art is a hobby. Therefore, you should go for something more serious. Great ideas, great vision resonates much better than a good technology. So if you have a really good technology, a good research, it's super important to communicate that with a larger body. Not necessarily just to boast your work, but because with a larger demographic or larger body who understands a problem, they will bring new solution that was not evident from the get-go. So my last podcast got picked up by Emirates Airlines.
Oh, really?
Yeah.
Okay.
So now if for the next, I think until the end of the year, if you get onto the Emirates flight, I'm the first one that just pops up.
Really?
I did not know.
Wow.
I did not know. My brother he sent me like, what the hell is happening? And he took the picture of the screen of the headrest screen. And like he was not looking for videos or movies. He was like just organizing things, but he just put the headset on already.
Yeah.
And then he's like, I started hearing a familiar voice.
No way.
And then all of a sudden she started talking about robots. And then she's like,
Oh,
but
really?
that's what my sister is. So he saw the screen and then apparently it was me.
Crazy.
So and then
Crazy.
that one I did not record for them. It was coming from elsewhere, but I obviously signed release forms.
So it's during the
Other things?
starting procedure in the plane.
Before the safety announcement. So
Okay. Wow.
you
Crazy.
might get replaced by this.
Well, not sure about that.
Or maybe Lufthansa.
Yeah, let's see. All right. So first of all, hello, Jamie.
Hello.
Great to have you here. Welcome to the Andreas Orthey podcast.
Yay.
So today I want to talk with you about reconfigurable robots. Basically, what they are, how to build them, how to actuate them, and of course, what they can be used for. But before we go there, I would like to dive a little bit more into your background. So currently you are a professor at the Swiss Federal Institute of Technology, and you are also the director of the Reconfigurable Robots labs there.
Correct. I am also the vice dean of the School of Engineering,
All right.
starting next week.
Oh, really? Congratulations.
Thank you.
Yeah, so I want to explore a bit how you actually got where you are right now and how you got to this point, and also what kind of things you accomplished along the way,
Oh,
because
wow.
there are so many things which you accomplished along the way. So let us start this journey right at the beginning. You are originally from Canada, right?
Correct. I was born in Canada.
Nice. And I heard also that your father is a scientist and
He's
your
a
mother
scientist.
is an artist.
Correct.
And I think that is really a unique combination of value systems, right? So can you tell me maybe a bit more about their professions and how this actually influenced you during your early years?
Right. So my dad is a animal scientist. He studied animal nutrition. For the large animals, domestic animals, so cows, chicken, poultry, and I visit his lab quite often, which was also the lab environment because he's doing nutrition, but also his lab included farm, which I did not appreciate as much because I just didn't find it to be too white. It was very much of in nature. And my mom, she's been painting. She does calligraphy for forever. And ladies' paintings are quite abstract. And yeah, so that's the household I grew up in. And
Nice.
my brother is economist. So we have quite diverse background.
So is he younger than you? Or?
Younger brother. He's academic as well. So my dad is a scientist and also a professor, retired professor. My brother is an economist, but he's also a professor. And myself also a professor. So
a whole family of professors, basically. Nice. And so your father basically studied biology in the first place.
right,
I
biology,
guess, right?
yeah, exactly, and
Okay.
nutrition, yeah,
Okay.
animal science. Yeah.
Okay. And he practiced in Canada?
He practiced in Canada. He did his. So my mom and my dad, they met in Canada while they were both students, and voila, I happened.
Yeah. Nice. And so basically your first big station was the University of British Columbia, right? So
Correct.
you did a bachelor there in mechanical engineering. So how did you actually decide on mechanical engineering of all the things which you could decide on?
Oh, good question. Actually, that was not my decision. I
Oh, really?
actually wanted to go to art school, fine art
Really?
school. So I had my portfolio prepared for admission requirement,
Interesting.
and I need a signature from my parents for sending in my portfolio, and they refused. So,
Really?
art is a hobby, therefore you should go for something more serious.
But your mother was an artist.
Correct, she was part of this decision.
Oh, really? So wow.
So I was sort of lost, and my dad told me, well, you like doing things with your hand, you like making things, you will be great at mechanical engineer. So that sort of shows how much of an understanding we had about mechanical engineers.
Yeah. And I mean, many of the great scientists, they were also like having like this artistic flavor. And so I think that like gives you like a unique advantage even.
Oh,
I
sure.
would even
Okay,
say
let's
maybe.
flow with that. I like it.
All right. But then basically you were denied going to art school. So
I was not allowed to go,
Okay.
so I went to a University of British Columbia.
all right, but why did you pick mechanical engineering?
Oh, well, that's because my dad said you're good with your hands, you like making things.
This is what you will do.
Then the closest thing would be mechanical engineering that we
right.
will allow you to go to. So
All right. And were you like excited or was it more?
no, not at all. I had no idea what mechanical engineering was about. But I figure it can't be that hard. Little did I know.
Wow. All right.
And I was always curious about everything, and this was absolutely the field I had no idea about. So I decided, okay, let's try.
And were you always like good at mathematics and physics or?
Right. I mean, I had good grades, and I was also the school champion to go to math camps or math
really?
competitions.
All right.
But
Okay.
I was not the strongest one. I wasn't the
But
strongest one.
you had a
but-
very good foundation basically. So you were
high
not
school
surprised.
foundation. But
Yeah. And so
I feel really ashamed to say I'm good at mathematics because I know I have nothing compared to my, math department professors. What we do is basically, exactly, it's math. It's not calculus. It's not profound mathematics. It's a tool that we learned.
but well, you use mathematics to change the world, so I think that is that is pretty great. And so I guess at some point you really fell in love with mechanical engineering, right? During your
Love,
studies?
hate. Let's put it that way. Love,
right.
hate.
All right. So at which point did you know that you wanted to actually continue doing that during the studies?
I never thought I knew enough, or I never felt like I grasped everything. More you know, like I think I think it's Richard Feynman who was talking about how to explain things, and it depends on the level of knowledge the listener audience has. So when you ask someone like, how can you ride skates on glass or ice? If it's a simple person, you say because you're wearing skates. That would suffice. But if you're talking to a scientist, mathematician, physician, the answers can get a lot more deeper, talking about the surface friction and how the temperature, like higher pressure, makes the ice melt. Therefore, it provides lubrication. So the answer can go deeper and deeper. And that's how I felt about mechanical engineering. Obviously, if you're a physics background, I still won't be able to explain to you a lot of things. Even mechanical engineering, I felt like everything that was taught or learned, I felt like there's more to it. So I guess the reason I continue to be in the field is because I felt like I didn't know enough. There's always more to learn.
So basically, your studies opened a small door, and you suddenly saw a whole universe of things which you could learn
I
about
didn't know exactly.
behind it. Nice. And then in 2002, you actually graduated from UBC. So what kind of options did you entertain at this point, and why did you pursue a PhD directly afterwards?
I'm not so sure this is a very inspiring podcast for the listeners, but it was a process of elimination. My
right.
friends went into industries. They often found, especially the mechanical engineering at the time, there weren't that many options. In Canada, we did not have automobile industry. We still don't. And if best I thought I wanted to go into automobile industry to design cars or design something that I can see being made physically. And that was not really an option. And a lot of my friends got a position in the industry that was very far away from quote unquote civilization. It was out in the mountains, out in the forests, near the oil drilling rig, deep sea. And I did not want to move away from downtown.
But you moved to South Korea.
That's right.
Well, that is even farther away.
It's a city, Seoul. And before it was Japan, I had an interview with Mitsubishi, and that's where I first moved to actually explore other options in quote unquote city life.
And so why did you, in the end, finally decide for South Korea and going to a research labs there?
So it was not a research lab; it was Samsung. So Samsung.
Oh. So you directly worked at Samsung,
right.
Okay.
So I was working as a research engineer. And the project was held in was a secret project then, building humanoid.
Nice.
And I like the aspect of secretness of it. And Samsung doing humanoid was not known and probably not spoken about even now. And so while I was doing the project there, the supervisor at the time suggested you're doing exactly the same thing what PhD student would do. Why not take classes? So I took classes and I got my credits in, I got my prototype working, and I decided I don't want to go back to the industry, and I was looking for other options. And apparently the other option was going for a postdoc, just continue staying in school.
And so when you started in Seoul, so was it already on the design of humanoid?
Yes, that was the project. That was the project that was sponsored by Samsung.
You worked the whole time on this project.
Right.
You didn't change directions or so during the time?
Well, it was first eyeball. So human eyes have 3 degrees of freedom. Not many of us know that. I didn't know that at all. I thought our eyes just go up and down, left, right. But it actually has a slight torsion that allows us to move extremely fast, effectively. Instead of going this XY curve, once you have this torsion, you go much faster for a large range of motion. And since when we are surprised and when we are alert, our eyeballs move at 800 degrees per second.
Wow,
so
I didn't know that.
Degrees of freedom are extremely important. It also allows us to see eyes with, when you say humans have eyes are a window to the soul, it actually makes sense because every human has a different ways of moving their eyes without conscious, right? It just happens automatically. And at the time that study was on, it was with a collaboration with a psychology department where they say the human eye movement can be studied to see their emotions. So you don't have to see any facial expression, but just using the eye movement, we can actually tell the emotions of a person. And they had a hypothesis, they had a survey, but they did not have actual proof. And the only way to make a proof of it is to show an eye movement that copies without having the facial expression. And that's what I was doing for initial project.
So you worked actually on the eyeball itself?
Yes.
Oh, really? Okay.
Eyeball simulator. And then that moved on to the hand and then the arm.
Interesting. And so was it, so what was your first paper you wrote?
The 3 degrees of freedom anthropomorphic human eye simulator.
All right. And so this actually worked. So you could basically see the emotions from the eyeballs itself.
Right. So I didn't personally, well, I wasn't personally involved in the human studies, but I was involved in collecting the data, or I used the collected data of a human eyeball where you can collect the data. We did not collect it with the eye tracker. We collected with a contact lens at the time. So we had a contact lens where it was tracking the human eyeball movement, and then we fed it into the how we are reading a newspaper article online, and then we fed it into the human eyeball, and then we show that it matched nicely and moves in the same speed, and we can really track human eyeball movement directly onto the simulator. Whether that conjured up emotions to the person who's looking at the eyeball, I'm not quite so sure, but we were able to.
So you're not an expert on reading emotions just from
not
the eye
at
movements?
all. Absolutely not.
All right. But do you think actually this technology exists in our smartphones? So basically, if I look at my screen, people could maybe figure out my emotions?
The paper's published, and it might be created somewhere in the marketing department. They tested out on a whole bunch of monkeys before feeding it back to us. That's not impossible.
Interesting. So every time I stare at my phone now, I have to be like very careful what kind of emotions I feel.
Or try to put in like extra winks in there just to throw it off a bit.
Nice. All right. And I think the arm and the hand you designed were very special because they were very lightweight, right?
Right. At the time, it was lightest for being like 3.7 kilograms total.
Was it also used on a humanoid robot?
Yeah, so not a humanoid, but it was the a guide robot on wheels with arms. So at the end, it was not used for carrying anything, but it was the joint design and the actual high degrees of freedom finger movements were used for other manipulation project that I was not involved in. But the arm and hand was used for a guide robot that was roaming around in Incheon airport for a while.
Interesting. And so what were actually the biggest challenges in the design phase to
So
make
at
it so
the
lightweight?
time, when the carbon fiber manufacturing was not very accessible for this project because they did not want to do a one-off manufacturing with this carbon fiber stuff. Either I had to make it myself, or it was gonna be made out of duralumin, which is a durable aluminum. So it was a 7,000 grade aluminum alloy, which is nice. It was not difficult to machine, but I had to find the machine shops who would do it. So the school machine shop or Samsung machine shop would not take it. So I had to personally go out in the field to find manufacturers. That was hard in terms of execution of the design. The design itself was tough because we were trying to pack in 7 degrees of freedom into the arm and then 8 degrees of independent freedom into the fingers. And more the degrees of freedom you have, more the motors you have to put in, and more the motors you have, the system cannot get compact. And we really wanted to maintain the same dimension as adult human, depending on, it was not Shaquille O'Neal, so, and it was also not my size, so it was very, it was tight. The clearance was tight. And the difficulty I had at that time that impacts me still is the cables. The fingers were driven by cables, and by definition, all cables lax. Under tension, they stretch. Even the non-stretchable ones. It's not the cable that stretches, but it's the grounding point that will stretch out or move. So that was a huge challenge because...
And so the decomposition of the robot, in the end, it was only durable aluminum or
Mostly.
okay?
Mostly. So I did not have to worry about the different levels of tension or the strain on different components because it was a very highly compact system. We really had to rely on the material itself to be robust, and that was considered to be completely rigid component. And
So how was actually your journey to get this material? So you said you had a lot of problems there. How did
material
you
was not hard. Like
how
getting
did
it
you solve
machined.
it in the end?
I knocked on every door of the machining street in Korea, Seoul at that time.
There's a machining street.
Machining street at the time, it no longer
Interesting.
exists
Okay.
because it was a couple of decades ago. It
Yeah.
doesn't exist anymore. Now they're congregated around Samsung area, but yeah, they don't exist anymore. And I was the only female they've ever seen in their store, it seems like. So I was blacklisted for someone who's asking for tight tolerance, impossible thing to machine. And yeah, so that was a huge challenge.
But then at least one shop basically fulfilled.
Oh, no. So I would divide up the tasks. So I will do some task in some shop.
All
I'll
right.
post-process in other shops.
All right. And then in the end, you had multiple shops, and then you
Absolutely.
basically got your material
Yes.
in the end. Nice. And then after you finished your PhD, you went actually to Paris to the
Oh, wow,
university.
you know everything. You see my diary.
Well, it's your biography,
Oh my
right? So
goodness.
it's everywhere. So yeah, so you went to the University Pierre Marie Curie, right,
Right.
in Paris. So what actually motivated you to go there? Did you already know someone there?
Not at all. I had to.
You just applied.
I applied. I applied about 50 labs who's doing robotics all around the world.
All right.
Literally.
So you didn't really had like a preference of what you want to work on next
Stay in the city.
in Seoul. Oh, really? Okay, so you were basically a bit disappointed that you didn't get something in Seoul.
No, but I think I was sort of avoiding the reality at the same time because I saw how my work in human anthropomorphic arm and hand ended up just I use air quotes here, becoming a guide robot where you don't necessarily need to have 7 degrees of freedom. Arm and 8 degrees of freedom hand to do a guide robot. So I saw that there's a huge gap in terms of what I'm able to design to what is actually going to be produced commercially. So I wanted to explore, if that's the case, I wanted to explore more what else can I do in this academia, which I had not much of interest beforehand, but now I had a little more interest to see how far I can design new stuff and see how they can potentially impact the world.
Yeah. And then you applied to 50 positions, you said.
Right.
So how many actually were applied?
I think I applied literally 50. I sent out my CV. But I did not have too many papers, publication list by then because it was a secret project. So I was not allowed to file any patent or write papers on it.
So how many papers did you actually had at the end of your
Not,
PhD?
I think I had like 2 or 3. But it was a
Interesting, yeah.
conference and it was very, it was not too descriptive about anything. So it was not, today's standards. If I published, if my student published as many as I did, it'd be difficult to graduate.
Well, different times.
Different times. Sorry, guys.
Yeah, but I think it's important to say that I feel that the difference in the work is not big, or even there is no really a big difference.
Right.
But the number of papers which are published is like a huge difference.
Right. It has become very clear to many. I think how we do research has changed a lot in the past decades. I always believe, regardless of the field of expertise or regardless of the profession, quality should come first over quantity. But it's hard to measure that in any sense. And being in academia, we are inherently in nonprofit organizations, and nothing. It's difficult to show ROI in your profession. So it seems like a lot of institutes measure your goodness and efficacy based on number of papers. So it's tough to just follow for quality over quantity. You need to have a better strategy in terms of how to publish and share the findings.
So I heard from some people, they say that quality actually comes from quantity. So you publish hundreds of papers and then you learn, you improve, you get better. And that is a way of how you can actually create something of quality.
That's true, but it's not the only way.
True. So then you actually moved to France, to Paris.
Right, I moved to Paris.
And there you worked on something very interesting, namely, a robot for laparoscopic surgery.
Correct.
Can you maybe tell me a little bit more about laparoscopic surgery, especially what it actually is and what the biggest challenges are?
Right, it's a process of doing minimally invasive surgery. Basically, you puncture holes instead of having an open surgery where you're supposed to expose all the organs. And often this is reserved for currently prostate cancer or prostate surgery, uterus surgery, or any tight surgical procedures where relative simple process in tight space within the abdomen cavity. You often, how you do it, you inflate this cavity with CO2 gas so that you would actually have a moving room. And the most important aspect of the surgical tool would be less than 5 millimeters in diameter and be dexterous. And most famous robotic tool we call Da Vinci by Intuitive. And that sort of started the commercialization or the popularization of robotic tools for minimally invasive surgery. My project was developing handheld tool that's robotized for surgeons who would prefer having a non-robotic surgery, but still having the advantage of using robotic tool. So with my developed robotic tool, it will be handheld, but it will have an autonomous and dexterity and autonomy to do a suturing at the tip of the tool. And it was developed to be under 5 millimeters in diameter and have enough of the gripping force to hold needle to do the suturing process.
So what is actually the suturing process?
Suturing process is basically stitching. You take a needle with a thread and you enclose the opening. That's too big to be cauterized with a bipolar or monopolar tool.
Okay, so what is a monopolar tool?
Monopolar tool, basically you send the current through the end tweezers or pincet, the forceps, and basically it will cook the tissue so that it will stop bleeding. So, but if the opening is too large, the cooking the tissue won't cauterize the wound, so you would actually have to do physical stitching around it. And often, I don't know the percentage anymore, but at that time, Da Vinci had, not everyone wanted to use Da Vinci because it was the first time this type of automatic robotic tool was introduced to surgeons. There was a huge market for surgeons who actually wanted to stage automation, where they want to do minimally invasive surgery, but a little more hands-on. And this tool allowed them to do this suturing motion, which was highly desirable to do so.
Okay, so and your tool, that was called JAiMY, right?
Correct. Yeah. That was not my decision.
but people liked it so much that they told you, hey, we need to call it like
so that it was a it was a collaboration with a company, Endocontrol, and the CEO decided they were going to call this tool JAiMY. And that was my Christmas present, the naming.
And can you describe a bit more the tool itself?
Right. So it creates a 3 degrees of freedom at the tip. So it's long about, depending on, I don't know how long the current laparoscopic tools are, but it's about 30 to 40 centimeters or long, 5 millimeters in diameter. At the tip, it has a forceps that can hold a needle. And then it would have a 3 degrees of freedom. So you'll bend down into L shape. And then it would actually, so that's 1 degree of freedom. And it can actually turn around the axis, but it can also have this rotation in this axis. So
and how do you control this? Do you have like
cable?
Cable.
Again, the cable.
Okay, and you have you hold it with your hand, or
You
is
would
it
hand
like...
it at the handle, and then that one was motorized. So you would have buttons and mini joystick that you can control to hold and rotate.
And so it's just this one piece, or do you have also a second piece, or is
one piece?
Okay, and the second
second will be just
a camera or something.
Camera will be third one, so your assistant will be holding it. Second will be another just a forceps that would be holding just to pass the needle on and bring it back. So one should be the needle holder that has all the degrees of freedom. Another one will be the one that's just passing around.
Okay, and this happens only outside of the body, right? So
inside the body.
Oh, so the stitching is inside the body.
Stitching, exactly. That's why the Da Vinci robot was highly desirable to do the stitching. The other things of a cutting or anything else, that can be done with the laparoscopic tool that's non-robotized. But the stitching, you actually need to do this stitching motion where you need all the dexterity. That we cannot do with a non-robotized tool. That's why the Da Vinci was so desirable to do the stitching. But if you could take the stitching out of Da Vinci, they could actually eliminate using the full system. At the time, I don't know what the latest statistics are.
So let me summarize. So basically, you have some CO2 which you pump into the body to inflate it. Then you puncture like 3 holes: one for the camera, one for like an assistance tool, and then for the JAiMY tool. And then you can basically do the stitching inside of the body.
Exactly.
Interesting. And that was used for actual surgeries?
Yep.
And so
it's
mostly
patented and distributed, and you can commercialize it, you can buy it.
Nice. And so what kind of surgeries are done
so
there?
Like prostate cancer or prostate
so is it only prostate or
prostate? So these are mostly desirable surgeries where you really do not want to do open surgery. You really want to do minimally invasive surgery. And uterus, gynecological surgeries, because this is really the surgeries that you really want to do minimally invasive. So those are 2 major market.
And so I think that is a dream of almost any researcher, right? So they do research and they bring it somehow to market, and it is in the end coming into a viable product. So can you maybe tell me, how did you actually accomplish this? So what steps did you take to get this platform all the way from research towards this
that's
product?
not my job. I did the research. I developed 3 prototypes of different kinds, different versions.
But was it already like something which the company...
company existed.
So endoscopic medical...
No. Endocontrol Medical.
Endocontrol Medical basically approached the research lab and said, "We need this. Correct. Can you create it?"
Right.
You created it. You gave it to them, and
that was my job.
And then you patented it, maybe.
Yes.
All right.
I wrote the patent with my supervisor.
Okay.
Yes.
All right. And then basically they took it and they commercialized it. Nice. And so do you have any...
Perfect partnership. I would love that,
nice. And do you have any statistics about it? So do you know how many of them were produced?
No, actually, I don't have the statistics, but the product still exists. So I think that's a good sign. I still get some checked at the end of the year.
That's nice.
Every year. So that's the...
All right. And then once you finished your postdoc, so what kind of options did you had afterwards, and where did you want to go?
I still did not know what I wanted to do. I still want to stay in school. So I applied for more postdoc positions. Again, 50 resumes, 50 CVs all around.
Wow. All right. And so how many did actually respond this time?
I replied to I said yes to the first one I got offered to.
Okay, and which one was that?
Harvard with Rob Wood.
Nice. All right, and so that was also a postdoc position.
Correct.
All right, and so then you basically came into contact with microrobotics. I
Correct.
think, right? So it was a microrobotics laboratory.
Correct.
Right. So what was your first research
Oh
project
yeah. I I told myself after, like I told you, the humanoid project or the anthropomorphic arm project, the biggest challenge was packing everything into very small packaging of human scale with so many degrees of freedom. And then I moved down to the millimeter scale laparoscopic tool, which was even smaller. And now I went to the microrobotics lab where now I'm assembling
Smaller
things.
and smaller.
Exactly.
Yeah, nice.
It was not intentional at all. And now I was working on Origami Robots under Programmable Matter project sponsored by DARPA.
And so you're currently still working on that, right?
Absolutely, yes, absolutely.
Yeah.
Yeah, it's a problem that keeps giving.
So just to summarize, those robotic origami structures, so they're basically self-morphing robots which can transform from a planar shape or something by folding, right? So can you tell me a little bit about the inspirations behind this? And
So I cannot take the full credit
Yeah.
for having the idea of doing the origami robot. The Programmable Matter was a project that was run by Professor Rob Wood and Professor Danielle Russ, who worked on this a proposal to say um, it's possible to have a material or matter that can self-configure like origamis do. And I was a new postdoc who was supposed to make a prototype to prove the concept. Eric Demain, it also was part of the project, who is a mathematician at MIT, just solved this giant mathematical proof saying that any 3D objects can be folded from two-dimensional sheet, a planar sheet, as long as the paper is large enough and as long as you can do multiple compound folds on top of each other. And yeah, so my task was to show this is actually physically possible.
And did you succeed?
Some part of it, the mathematical formula basically says you can fold concave in, concave out, whole round surface, any shape and sizes. Obviously, that requires large meters of paper, square meters, tens of square meter of paper, just to fold a shape of a table or a chair to recreate the curvatures and dimples altogether. My work was a cute airplane and a boat.
Really, I would think that this is more complicated than a table or so.
Again, it's a paper airplane, paper pyramid, a boat. It has a certain number of folds. Whereas if you're trying to create, I'm looking at the sofa there, so which has a lot of design. So when you have a curves, nooks and crannies, that would create a lot more fold to create that. But if you're doing a very simple a tent or a fold-out chair, I guess that's a lot easier.
And so what do you actually think are immediate applications of this?
There's no immediate application of folded airplane or boat. However, the components of the joint design, components of the mixture of heterogeneous materials, the use of the interesting combination of transmission combined with different type of actuation, those components can be applied to any type of automation or actuate a system that is looking for a new solution to bringing down overall volume and weight in high degrees of freedom environment. What excites me about origami structure is that, first of all, it's a folded structure, So normally it changes a lot in terms of the form factor. You can have a large tent being sprung out from a small packaging, thanks to obviously tensegrity structure, which is based on a spring tension or a steel tension with cables, but also often origami structures like umbrellas as well. It has a large form factor of being able to create a semi-spheric shape about a meter diameter from a stick format. These are possible because you're changing the form factor from folded position to the large deployed position. And that we can take away to, you can take that inspiration to apply into the joints that are often used for folded chairs, folded microphone holders, a telescopic boomsticks. So these are the things that we can take away, and this is why I'm trying to use it for my reconfigurable systems.
So your vision would be basically to have one general purpose robot which can like shapeshift into any kind of structure you want to create.
That would be great. I'm not so sure how much of this is as realizable as I want it to be. But one day, if we can have very specific environment, these are the tools that I can immediately use. And until then, the components would definitely be useful, especially this era of large population of humanoids.
That's true. And so how do you actually control and actuate some Robogami so that it can actually shift its shape from one into another?
Right. Good question. Unfortunately, we don't have one way of achieving this. The latest paper, we talk about a very specific way of achieving large degrees of freedom, large potential applications, and large range of motions. Those are very difficult things to do with a single degrees of freedom, a single way of controlling. So what we show is taking advantage of traditional leader-follower controller, taking traditional, I use air quotes again, a classical marker-based motion capture system. We combine that together. So having modular systems, it shares all the connecting part with each other so that it can be assembled and disassembled at will. And we apply this algorithm as well as we share the same micro controller and electronics that allows us to apply the same control method to any modular system. So what we can do is the same electronics, but kinematic is different for every modules. And this allows us to motion teach by demonstration.
All right. But don't you run into the problem of like local minima where, for example, you fold something in such a way that suddenly different parts block each other?
Good question. Yeah. So first we depend a lot on the operator to motion teach already, because if the trajectory or the task is very clear, then we assume the operator knows what he or she's doing in terms of creating this demonstration that we want to teach. However, if that's not the case, we also have a prevention mechanism where we don't want to destroy these modules. So we can actually give pre-orders and preconditions of putting the maxima or minima of the torque, range of motion, trajectory. For example, if you want to work with a human operator, you don't want to attack the human operator. So we are able to put this a maxima or the condition to the buffer into the controller.
So another way you could actually solve that could be like this motion planning algorithms, which give you like very hard guarantees that they will find a solution if one exists to go from one shape to another, right?
Right.
Do you think this is viable, or are there too many degrees of freedom?
It's absolutely viable as long as you can have 100% confidence level that all your modules are going to work the same. So in the ideal case, and mathematically, we already shown the potential optimization loop of how many modules you would need for which task, how and which configuration you'll be running in, for energy optimization, minimum trajectory, planning time, and the fastest task completion. So that paper was
Mhm.
a couple of years ago with Professor Meibao Yang, now Professor Meibao Yang. So that was fun. But we knew already when we were writing the paper that this is not physically viable with the current modules that we have. Not because they're not, commercial level prototypes, but because we optimize the size and the motor selection for its overall assemblability.
Mhm.
So it was optimized for easier assembly rather than robustness of the system. So the
Mhm.
battery did not run as long as you needed to run these type of experiments. So if you were to restart the same modules again, maybe we'd be able to show the optimization process on a physical platform. But yeah, so that's the next thing we need to work on it with the next hardware platform.
But you think it's better basically to design controller which move you from one known shape to another known shape, right? Instead of like planning this motion for all the different degrees of freedom.
Not necessarily. However, I always work with the premise we don't know what's going to happen. So
Sure.
how do we know what the task is going to be, which environment it's going to be, and how many modules do you have alive?
Mhm.
This is a serious question because, again, not all the modules are always going to be alive. Not all modules are going to have their GPS signal working.
Mhm.
Not all modules are going to have Wi-Fi working. Not all modules are going to have the communication working 100%.
Mhm.
So these are the questions that's more exciting for me than, oh, what's the perfect configuration for this task that's already known?
Mhm.
It's more exciting for me to look at how well this is is it gonna survive and execute this task somewhat, even with a broken module?
Mhm.
Is it possible even? So this is the question I'm more excited to looking at.
Yeah, interesting. And you also mentioned humanoid robots just a minute ago. So yeah, right now, of course, there's a big push to bring like millions of humanoid robots to our factories and homes. So it seems sometimes that this is basically everything we need to solve all the human tasks which we have in our environment. So why do you think we still need, for example, reconfigurable robots in that scenario?
Because I don't think humanoids are the best form for doing a lot of tasks.
Interesting, but I think evolution would say otherwise.
That's true. I said humans are, but not humanoids.
All right. So you think there's still a like large gap between a humanoid robot and a human? Do you think it in terms of like hardware or in terms of software?
Software is amazing. I think any software will be better than I am in doing anything. However, physically, unless we're gonna clone ourselves, hardware wise, definition of hardware for any system is it needs to be. No, let me bring that back. For designing anything, we don't have uh, the same type of motors or same type of actuators as organic being, and that actually means that we need to decide what we take away from existing off-the-shelf components. And when I say off-the-shelf components, obviously we're not going to Home Depot to pick the motors for next humanoids. We will be designing these, but there is a physical limitation to how we are able to build motors and sensors. We have seen huge growth and improvement in making memory chips, following Moore's law. But we cannot expect that from the capacity, the motor capacity. It's just a purely different physics. So it's a law of physics that just dictates how these motors are developed. So that means that we have to create an abstraction of what we want. So currently, we have a version of humanoids that's able to grab some things, pick up some things, move in a certain pace, and deliver some tasks. Yes, one day they'll be developed enough to deliver, more things, but it will never be as good as we are. It's not just the size, it's not just the timing, but it's not going to be as good as we are. But there's going to be super useful because at the end, most people probably don't want humans to do everything. We want them to do things that we don't want to do, and so that it will give us more time to do things that we want to do.
But I think for people outside of the field, it seems that this gap is very small. So there are humanoid robots which can do backflips.
Right.
I guess someone who would just naively watch those videos, they would basically say, hey, we are almost there. Where the gap must be super small. So what is actually still there which differentiates humanoids and humanoids?
So I'll try not to put my hat on when I wrote my anthropomorphic robotic arm and hand decades ago. The gap will continue. It will always be there because we're not cloning ourselves. So it's not like we are going to be able to create everything that we're able to do. I think the biggest gap exists in a task that we think is super simple. That's where backflip, for example, taking garbage out and making sure that your plastic bag does not rip while you're tying the garbage bag, the top of the garbage bag. I try to save my garbage bag, the taxed garbage bag, so I try to squeeze in as much garbage in it before it goes out. That's not going to be possible with a humanoid for a while. Partially because it's not the motor problem, it's not the gripper problem, because I think the grippers or the manipulators are getting better and better every day. It's just that we don't know how far the motors or the hands should push down to the garbage so that the plastic won't rip.
But wouldn't that be a software problem? I mean, I could imagine myself wearing like a telescopic arms, and I would try to do this task, and I could imagine myself
succeeding. Would you be able to? Imagine if you have a 2-meter long stick.
Yeah, I imagine myself with a 2-meter long stick and trying to actually close the garbage
Even
bag.
So would that be?
I think it's
you need the
doable,
subtlety.
no?
You will feel how much of the plastic is giving. It will stretch a bit. But as humans, we will know when it will start ripping, and when it is just enough that you can push a little further or not.
So I'm not 100% convinced, but yeah, I see your point, and it's a very good example.
And currently, there is no sensor that's able to measure this. They can measure individual garbage, their property under material tester, but when you have a whole bunch of stuff in that garbage bag, that's organic, non-organic, hard, not hard, semi-soft, food still there with a skin on, no skin on, bones. It's a disaster.
So basically, your take is it's a sensory problem.
We need better sensors. We need better fingers to tie this. We also need the process of taking the garbage bag out of the garbage can. Without ripping the plastic.
All right. So let's get back to the microrobotics lab. So you basically started your new postdoc, and at some point, I guess you wrote again 50 applications, or how did it work afterwards? So what were your options there? What did you do after you finished your postdoc?
After my so I loved Rob's lab. It really felt like where I could investigate any question that I may have on any topic I want beyond robotics. Any question I have in terms of science, I may not find the answer, but I definitely knew where to go to find out more. And I love that environment, and I actually wanted to stay. And Rob told me, JAiMY, You need to do more.
Okay.
And it was Rob who recommended and pushed me to, go for a permanent academic position.
And so how many applications did you send out?
2.
Two this time. Okay. So nice. And you were you got
And
a reply?
I did well. So I interviewed 2 places, and I really liked EPFL.
Mm-hmm.
The group of professors I talked to was super clear that they wanted to have me explore further things that's very unconventional, which was self robotics at the time.
So you basically moved to Lausanne and you started your Reconfigurable Robots lab.
Yes.
So what kind of challenges did you take on in the beginning?
Being a director of lab, it's a big title for someone who had no idea what that meant. And then the first challenge was they wanted me to give a name of the lab, because it was system-wide, administration-wise, it was critical that they need to have a lab.
Mm-hmm. And you didn't know?
I did not
at that
know what my
point.
lab's going to be called, so I wanted to call it a Transformers lab, because I knew I wanted something unconventional in terms of robotics design, robotics research. And the movie had just come out, the Transformers movie, so I could not use that.
Mm-hmm. And so how did you actually structure your lab? So did you like try to enforce a certain culture there, or did you have like a big lab vision, or how did you organize yourself at that point?
I guess I did not have active intention, but I guess I wanted to emulate the research environment that I was in before. So I appreciate my group at Seoul National. I appreciate my group at Harvard, in Paris, and also as a bachelor student, I also worked in a lab of Elizabeth Croft's lab. So I really enjoyed all this experience in different countries and institutions. So I think I wanted to create that environment. But I don't think I had an active consciousness to let's do this. But I think it was somewhat embedded.
But if I would have to say, so internationality was definitely a value, right? And also you mentioned like that you like this openness of the micro robotics lab. So I guess those are also values which you try to not enforce, but like try live by, right?
Right.
Yeah, interesting. And so what kind of projects did you start off in the beginning?
Good question. What did I have? Oh, yes. I was part of the NCCR Robotics Consortium. It was a national competence in National Center of Competence in Research. And my colleague, Dario Floriano, had just got this ginormous funding in. And I was actually hired under that scheme to EPFL. So I really thrived in that environment where I was able to work, or at least not work with everyone, but at least I was in the consortium together with all the top robotic researchers of Switzerland at the time. We still are, but at the time I was, as a complete young faculty member, I was immersed with all their work as well as their vision for robotics. And that really gave me a huge boost in my understanding of how academia works. Or I guess that's a huge statement, but how research circulates with consortium of highly talented faculties, and how collaboration brings a bigger goal into
So
reality.
how does it actually work? Tell me.
Okay, I take that back, but that it's
Or
a
what
long,
did you learn there?
yeah, it's a long process in terms of the ideas come together, and also good ideas resonate with more people than a good technology. Great ideas, great vision resonates much better than a good technology.
Mm-hmm.
So if you have a really good technology, good research, it's super important to communicate that with a larger body, not necessarily just to boast your work, but because with a larger demographic or larger body who understands the problem, they will bring new solution that was not evident from the get-go.
So you would say you need to first go viral before creating the technology, or do you think that there's a connection there? So how many people you actually influence with that? That is like a measure to how useful your technology is.
I hope that's not how it's measured, but I hope I hope I would like to no, I don't think that's I hope that's not how it's measured. I hope that's not how it's measured. I hope the importance of project is should never be measured by how popular it is. However, I should never stay naive thinking that the problem is as big or small as we perceive it.
Mm-hmm.
But if we had, we should always have, ears to hear others' opinions. But it's always it's important to have our own integrity. Because from my colleagues who talked about their problems, their vision and motivation really motivated me to see how I formed my projects.
Mm-hmm.
So that was quite important for me to. I think that made a huge impact in how I conducted my research and how I formulated my research questions.
Mm-hmm. So going viral is not the only thing which matters, basically.
It would be great because going viral, if going viral really depended on the goodness of the project or the problem, definitely that would be something that should be considered from the day one. But currently, I don't see the logic of what goes viral and what doesn't go viral. I don't understand how that works yet.
Yeah, but I mean, it's very difficult to go viral, right? And
Right.
somehow you have to like access some kind of like
Right. That
part
I
of
don't.
human nature
Right.
which really resonates with people. So I think you can only do that if you maybe created something of quality, or
I hope so.
maybe that's not
The only
necessarily
criteria.
true, right? But yeah. Okay, let's talk also a little bit about soft robotics. So in my mind, soft robotics is connected to reconfigurable robots by basically increasing the number of joints, the
Yeah.
degrees of freedom,
Yes.
until you effectively
Yes.
reach an infinite number of configurations you need to control. So do you think about it in the same way, or do you think soft
Absolutely.
robotics is
Absolutely.
different
I
in your
sort
mind?
of started making more definite link with Origamis, Robogamis, and Reconfigurable Robots, Reconfigurable Systems, and with relations to soft robotics, because I've been part of the community from day one. So I relate very deeply with the soft robotics community. But if you were to ask, oh, but Jamie, not all your robots are made of soft materials like silicone and rubber. That is true, but that's not the only way I see soft robotics. The soft robotics really accentuates the ability of your robot or its platform to adapt to the environment through its material compliance. But it's not always the material compliance that's important for the robot to adapt to the environment. Softness can come from the obviously material that's innately compliant. Design, any material is soft and flexible as long as it's thin enough and long enough. Diamond, graphite can also be flexible and soft if it's thin enough. So through design, and third is through control. And so these are the three aspects of the softness I address through my research and reconfigure robots.
And so, why do you think we need soft robotics? So I think if you look at factories, people want to have like very hard robots which go like precisely to like a millimeter correct position.
True. That's super important. That's how the automation came to the picture of industrialization. We want to have machines to be faster, more accurate, precise, and efficient than human workers, and so that we can do other things that's more difficult and challenging. But that's not the so that's the period of automation, which is very important. And it turns out when you want things to be stronger, faster, and more accurate, they have to be made completely in a strong metal material.
Mhm.
But those machines stay behind doors. They stay behind the authorized personnel only door panel. We are living in 2025 now, going toward at the end of 2025. We want more. We are living in an AI generation, and we expect machines to come out of the factory closed doors. And you want these machines to come out in our daily living lives, living room, actually, in our home. So first of all, these automation machines, robots, won't fit here. Just won't go through the door. And even if they were to go through the door, you don't want machines that's moving at that fast speed and torque,
Mhm.
swinging around you. So to match the environment, which means the size of our homes, size of the operator, which is us, the dimensions have to match.
Mhm.
Second is its work resolution. The space, not only its own physical space, but the resolution of their activity have to match. So before, if they were spraying or moving objects from 2 meter distance or displacement, that will come down to much smaller scale, a centimeter scale. And third, it needs to match the compliance of the operation around it, which means its range of motion, the how far it's moving or how far it's executing a task, has to match the range of motion that human operators are around. And it's not just human operators. Domestic animals and babies, they are
Mhm.
also another considerations. So I'm not necessarily saying all the robots within households and in a human environment needs to be soft, but it has to be adaptable to this environment. And soft robotics community really highlights exploring different material choices and control methods.
So it's mainly a safety aspect. That once you go into a human environment, you need to be
Safety
soft.
and efficiency.
Mhm.
If you're trying to wash dishes and if you were to break it,
Well,
you're failing that mission.
that's true, but I think that you could also do with hard robotics if you're like millimeter precise, but maybe. Um, all right, so we already talked about Robogami, which I guess is one type of reconfigurable robots. So how do you actually think about reconfigurable robots, like from a more abstract point of view? So how would you define them? What are maybe some examples in your mind which go beyond Robogami?
Right. So robogamis are basically the concept of building robots that can self-fold into different shapes and forms. Obviously, if you have a single platform, then you have a limited workspace, limited size because it's just bounded by its own size. So if since I want a system to reconfigure and adapt to its different task space, we started thinking about can we make things modular,
Mhm.
making foldable robots to be modular. And the smallest unit of a polygon was triangle. So that's where we started developing Mori, modular origami robot, where modules serve as building blocks for reconfigurable robots. So think a flat Lego block that can assemble uh, and disassemble according to the required task. And one of the projects, the major projects, was sponsored by European Space Agency, who liked the idea of having working blocks, robotic blocks that can be stacked together to be transported to different space
Mhm.
and be assembled with how many modules you require for a given task. So we have shown that it can be used as self crawling robot, quadpad robot, um, uh, uh, a haptic device that transfers force feedback. So we've shown a couple of examples of how 4 modules can move, 6 modules can assemble to do the different things, 10 modules to do locomotive motions.
So you would say space applications are one of the most exciting fields.
Right, because it also is going to be a microgravity environment. So you're not so bounded by their gravitational weight of many modules.
So I think one aspect which I always find a bit difficult. So I can imagine that something morphs into different shapes, but very often we have like very specific technology for things. For example, we have like speakers, we have microphones. So how do you think about this? So how can we maybe even reconfigure ourselves to do those more narrow tasks?
Good question. I think one of the things that we can immediately think about is humanoids. Currently, there's a limitation of, I mean, they do amazing things, right? They, like you mentioned, Boston Dynamics, they do backflip, Unitree robot dances and does is able to dance better than I can, or remembering all the steps that they say in Austrian waltz a ball. So, but they cannot do everything. So immediately we might be able to give these humanoid robot, which brand you might choose, a tool. Give it an extra tool that currently, if you're using conventional manipulator, you have a fixed manipulator to do manipulate fixed objects. They're bounded by size and dexterity. Imagine giving them a different changeable tools of manipulators, and they can change by themselves. And if not manipulators, they can have their own proper manipulator where they can change the end effector to do a different task. So, for example, humanoid that has a hand for walking dog and different hand for doing the dishes, a softer one. And you have a different one for taking the garbage out because it needs a stronger grip. So that's one of the things that you can think about adding the reconfigurable robot under the frame of creating different manipulators.
So you also think about it in terms of like the tool itself. It's just changing maybe from a screwdriver to a sponge
gadget
or
arm.
something.
Yes, a bit.
Go gadget.
Go gadget. The gadget, Detective Gadget is a cartoon that I used to love watching.
I don't know that one. So that is a detective who has a shape-shifting tool.
Who has under his a trench coat, he has a hand that changes from like a Swiss Army knife that has all the tools coming out. Under his hat, he would have a quad pad, a helicopter coming out, and he can fly around.
That sounds funny. All right, so let's talk a little bit about the expertise you have in your lab. So, of course, robotics is really an interdisciplinary field where you work at the intersection of many different domains. So, what kind of engineering fields do you think are actually the most important ones for robotics?
I think they're all important. It's so. Disclaimer is at the time when I was in school, we did not have a degree in robotics. It's recent thing. So my degree is in mechanical engineering, like I said before, and it's quite recent for my school. The master's program, a master's in robotics, was found about 7-8 years ago, and PhD in robotics was found 15 years ago. So it's quite new domain of studies. So that being said, I think robotics inherently stays in a very interdisciplinary field of studies. And in my group, we have engineers who did bachelor studies in mechanical engineering, electrical, computer science, even mathematics, pure mathematics. So I have open doors for these students who's contributing tirelessly and extremely brilliantly in their projects.
But isn't it difficult to bring all those fields like together to work on like one project?
That is true. So I think that sort of drove the culture in my group where everyone is responsible for two papers. One is their main paper,
Hmm.
and the second is they were their second author, where it's a collaborative project with their colleague. And often my job is tell them to drop one or two because they often come back to me asking, Jamie, I want to work on these four projects simultaneously.
Hmm.
So it has been working quite nicely in my group.
So basically, you don't have like a required prerequisite for students in your lab. So it really depends on their background. And
Yes and no. So they first of all they have to be interested in it, and often when they're interested in it, they either have their own personal project that has some level of expertise in programming and hands-on experience
Mhm,
and robotics, but not necessarily a degree on it.
mhm. So you would say basically passion is the most important things for students.
Exactly. Yeah.
And so if you look at the future, so what do you think will become like more important fields which will influence robotics?
So I really believe we are exploring, we call this robots, we don't call this automation.
Hmm.
Um, the reason is robots are basically the very intelligent machines that mimic what we do. It doesn't have to look like us, but mimic what we do and is doing the work for us. Um, because robota basically is a Czech word for labor,
Hmm.
and that's how robotics came into our society. The robots inherently do what humans do. It doesn't matter how they look like. They're invented and they continue to be developed because we want them to do what's necessarily for us and society.
Hmm.
That being said, where we go in this world of fast changing technology, I think we don't know what we want to do or what we are doing.
Hmm.
In order for us to better control, better build, better design, and better propagate technology in robotics, we need to know what we want and what we want to do with them. And that we don't know quite nicely yet. We
Hmm.
have psychiatrists, we have psychologists, we have neuroscientists. We're just finding out how our brain works, what connects us, how we operate our limbs when they're all functioning, some when they're not functioning as well, how we operate them, what we feel, how we move. This is studied, but not excessively. And how that connects to our efficiency, emotions, efficacy of how brain works compared to how we interact with the environment,
Hmm.
visually, audibly, and physically. That's not quite known yet. So immediately, I'm interested in how we experience things, how we move in terms of with object, without object. And for us, how we experience things currently is highly, highly dependent on vision.
Hmm.
We visit places, we taste things without tasting, we go to places without visiting visually. We see the videos and we hear things without audio. But it does not replace a physical experience. I would like to see how far robotics technology can take us to experience things too. Not necessarily I want to create more couch potatoes, but because things that we are experiencing now is quite limited and we sort of forget what experiencing things are like. And I'm saying it's robotics. It's never going to replace real experience, but we can actually see, oh, this is not a real thing even further.
Hmm.
And I want to see what that's going to be like. And for that, I need to understand more how we function as humans.
Yeah, this brings us to a very interesting topic because you're also working on haptic devices, right?
Exactly.
So they are often inspired by origami folding,
Right.
I feel. So can you give me a quick overview about them and what kind of physical variables you actually are able to measure with them?
Right. So, um, currently I did mention that we don't know exactly how we feel things and how we interact with the environment. the reason I said that is we know what the material characteristics there are, and we know how much force is applied to certain surfaces or not using force sensors and material testers. However, when when you're talking about the complex environment like squishy plush toys, soft cushions, firm handshake, ripe peach where the skin is about to peel off, those data don't exist. The reason is the sensors are highly customized for very specific tasks often. Force torque sensors that's attached to the end effector of the robotic arm is developed for testing out different gripper manipulators' efficacy, but not necessarily for handshakes or manipulation tasks that we do daily with groceries or interpersonal relationships. So for that, we need to understand the softness, not the hardness, material hardness, but the softness. And softness is only measured. It's a very complex because human is complex and human anatomy is complex. But largely, it requires two feedbacks. One is cutaneous feedback of the skin, deep, and kinesthetic feedback, which is felt by your bones and muscles. So you can only experience things fully, tangibly, if your skin is touched and you're moving your fingers or arms or anything else. So unless you move and touch, you don't feel full-heartedly. How do you know that? Because when you see an object, what do? You knock on it. Just touching is not enough. You can get the temperature a bit, but if you want to figure out if something is really hard and if you want to feel if it's made out of wood or a concrete, what do? You knock on it because you need to feel the vibration and the texture at the same time. Currently, until now, there was no device that's able to even emulate what this is like because we need to both create this feeling of the skin being touched and the kinesthetic movement. And I wouldn't say it's now 100% possible, but we've seen certain levels of it where we can use these platforms to collect more data and improve further these designs.
So you also worked on something which is called the softness rendering interface. So is that basically the one you?
So our softness rendering device called SORI is able to give our skin the sensation of being stretched and touched while providing force feedback to give a materials hardness feedback. So you can normally, if you give a force sensor to sense ice cream sandwich with, you know what ice cream sandwich is? Basically, you have a hard crackers on top and bottom and soft ice cream in the center. And then just ice cream is just soft altogether. If you were to give this to a force sensor, the reading is going to be the same because the hardness will be the ice cream until it breaks, the cracker breaks. The hardness is basically the center ice cream because the displacement is going to be the same. So basically, force sensor will tell you that they're both ice cream. You will not detect the cracker on the top.
And so you basically need the vibrations.
You need to have the skin to feel that it's not going to be able to dip toward into the ice cream. So it's not the vibration. It's more of a contact area change of the skin.
Okay, so the variables which you need to
recreate
are basically the vibrations of
vibration is the texture. We are not even talking about the texture right now.
Okay.
We're talking about the softness rendering. In order for the softness, it's not if you want the scratchiness of the cracker, then that will be the vibration. But if you want to understand how soft the interface is, you need your finger. Oh, think about the memory foam. How do you know your memory foam is soft if you were to have a book on top of it? You won't know if it's soft because book is hard. You only know memory foam is soft when your hand goes in, and the foam goes in between your fingers. It goes out in between your fingers. You have a higher contact area than when you have the book. The book goes down, you understand the actual material characteristic of the memory foam, but you don't feel it's soft. Because softness is measured by the indentation of the system.
And so with the software rendering interface, are you actually already at the point where you can
decipher the ice cream sandwich
or
from
emulate like anything, any object, or is there still like something which is
not everything, because it has a limited maximum force we were able to render, and has maximum surface area we can cover a single finger. But we are getting close.
So basically, you have to wrap the whole body with this device,
right? Because how much you feel with a single finger is going to be different psychologically if you're using your whole hand. Like,
and so what kind of force ranges can we actually detect, and what kind of force ranges can the interface detect?
It depends on how big we can make the interface. So we can pretty much build the same level of force. But what's more important is that how much of surface we're covering and how much of resolution we can create.
And so you think you're already there, or what is actually not
single
missing
point
now?
of a single finger, we're able to do that for that resolution of a single finger size resolution. But if you're looking for a resolution that matches actual sensory resolution of finger, this is going to be a couple of tens of thousands of the resolution point. Now we're playing with the brain now. Our brain gets tricked very, very fast. So even though our eyes can detect a lot of images, if you were to give 8 frames per second, you already feel like it's continuous motion. And same thing for our sensor. Even though it has a lot more dense sensory feedback on the fingertip, you can sort of trick its distances to show it has a higher resolution. But that's a future work to follow in terms of what are the tricks you're going to use for this abstraction of resolution.
Yeah, interesting. And so what kind of applications do you have in mind for that long term?
Now you can send your humanoid for a shop for your perfectly ripe avocado.
All right. Yeah. So avocado shopping
Avocado
is the next
shopping.
frontier, basically. All right. Let's talk also a little bit about AI tools. So I think AI has really started a big revolution, and millions of people are using tools like ChatGPT. So how do you think did AI influence actually you yourself, and how do you actually use AI in a research setting?
Absolutely. We use AI for. I might offend people here, but it's a really good pattern recognition tool. So a lot of soft robotic systems, whether it's made of soft materials or not, is completely nonlinear in its behavior. So it's very great it's extremely helpful when we have an AI tool to make sense out of the very nonlinear behaviors. But I still believe strongly that having analytical model for our very nonlinear behavior robot to figure out its behavior based on analytical model of joints, transmissions, connectors, soft sensors, inflating interfaces. So we're trying to use analytical tool-based system where the in between the black boxes are analyzed by AI tools.
Okay, and so like personal, do you do research differently in a time of large language models, or did the way you approach research questions basically have stayed the same in the last 10 years, 10, 15 years?
Research question remain the same. How do you make, design, fabricate, test, experiment different robotic platforms to potentially have greater impact in society? That stayed the same. How we build it, how we design it, how we test it uses extra tool, which is in the form of AI. Now we have a new research question that's quite recent in my mind is that how do we use our new platforms to collect better data, test data sets that already exist, and create platforms that is more accurate to use or apply interaction with robots or interaction with human in the loop, because these data don't exist because there just was not platforms to test it or collect it. And I think this Reconfigurable Robots are a good blocks and platform to test new data sets or create new data sets.
Okay, creating data sets and learning from them is basically, in your mind, the biggest application. And it's not that you're using maybe like some AI agents which are doing like some deep research for you in a very specific niche.
I wish
field
they
or
could,
so.
but it's just that they don't know. They don't
Yeah.
know this. Their current data sets that exist and current knowledge that these AI agents have is based on what others shared. No one has shared this.
No one had already like shared the answer to this question which
Exactly.
you are searching for, right? So all right, so in your mind basically AI tools are very good pattern matching or like an associative memory where you can basically have access to all the knowledge which humanity has already produced, right? But once you have like something new which you want to solve, then it's becoming more and more useless, I guess.
I would like to teach AI to be smarter. I guess that's what I'm saying.
Well, yeah, that's
Provide them with more tools and data.
yeah. So you are, of course, also dedicating a large part of your day to teaching. And I saw that you also like published a bit about it. For example, you published a paper about project-based learning.
Oh yes, yes.
So I guess you're very dedicated to like doing a good job at teaching. So can you maybe like elaborate a bit on your approach to teaching and what you do differently maybe to other people?
So my job title is professor. So and I'm in academia, and it takes the found knowledge and research should be passed on to the younger generation. And to me, the class that I enjoy the most was a project classes when I was in school. And I think this is even more pertinent for the new batch of engineers who's graduating from engineering school. The reason is post COVID, a lot of administrations and policies realize education can be much cheaper by putting everything online. And unfortunately, a lot of measures that was taken during emergency measures that was taken during COVID period sort of got stuck. But like humans learn so much more once we have a hands-on experience. To me, manufacturability is not 3D printability. Those are not the same thing. And assemblability is not what's possible on simulation window. It's literally how you can assemble it in real life. And these things you are not going to be able to learn. And those are just the tip of iceberg. How you design, how you collaborate, how you make a system. It's difficult to understand and project if you've never built anything in your life or in the context of in an engineering school. And that's why we are trying to teach in these classes. Not necessarily teach how to do it, but to teach that there's so much that's hidden and challenges that's not evident if you do things online. And they get to experience these challenges first-handedly. And then these are the topics that I like because it's a project courses. One is for sustainable future. So this is targeted toward mechanical engineering students who has a background in mechanical engineering design, and they're supposed to create design product that's gonna build a more sustainable future.
And so how can I picture this? So how much freedom do the students
They have
in
absolutely
choosing?
full freedom in
Full
choosing
freedom.
in their project, as long as they're not talking about materials. They are not allowed to say this is made of a sustainable material. The reason is they're supposed to use their degree. So you're not getting a degree in material engineering. That means you're not allowed to talk about materials. You should not depend on others' expertise to make your product sustainable. They should use their degree, their studies to make product
All
more
right.
sustainable.
And how does it actually work in a practical setting? So basically, do you meet with them like once a week and you give
Right,
like some
so-
guidance, or is it like just give them a topic and they come back half a year later?
Yeah, they wish. No. So we meet every week. So they get certain lectures, and for the first hour, an hour and a half, and they have other hours to start working on their project in a group of 5 or 6 members, and we meet every week for getting updates on their progress of project, and we gave them hard deadlines on making decisions. Making decisions is hard, and it's because they have to be responsible for the decision they're making with the information they have up to that time. So making hard decision is one of the biggest challenges I think my students have. They're all very brilliant, and they really want to optimize for every single aspect of the project, but the time comes they need to make a decision on a certain aspect of the project, and that's one of the things that we try to enforce. That hard decision, you cannot go back. Imagine this is where you need to give orders, send it to your subcontractors, and this is where you have to move on. And if it turns out to be a bad decision, they have to own it and make the best case out of it. And that's how the project course moves on. And that way, they have, at the end of the 14-week class, they all have a working prototype. And for the past almost 8 years, there was never a case we had a demo effect, which means demos don't work. But none of the all the demos, 100% worked on the demo day.
Wow.
So come,
that's
it's
quite
a
an
last
accomplishment.
It's last Friday of every semester, so like a week before Christmas. So you're welcome to come to our open house demo day.
Interesting. So yeah, we talked about a lot of accomplishments. So what would you say actually in your mind is like the most important accomplishment in the last couple of years?
I think it's my students who are now industrial leaders, head of the R&D, professors, spin-off CEOs. They're so amazing in every front, regardless of which path they decide to take right now. They are making a huge impact in their community and spreading their knowledge of robotics or beyond robotics. And these are things I never expected to be my biggest accomplishment. But this is the impact I'm making. Not necessarily my robots in their form, but how these robots impacted my students to go out there to build other systems out of it. Systems meaning not only the technological systems, but they are spin on those knowledge to do what they're doing the best in their current positions. So my students.
Yeah, that's a nice answer. So and project-based learning basically works apparently.
I hope so. I
Yeah.
hope so.
But I guess it's also because you're a good mentor and also a role model for those students so that they can actually accomplish so much, right? So talking about mentors, so do you think there were like some influential people during your career which really influenced you deeply?
Oh, absolutely. Everyone influenced me one way or another. My mentors, my supervisors who's giving me positions, giving me projects to work on, had the patience to wait and had sharp eyes to ask questions, give me guidance on different academic questions to life questions. They definitely formed me immensely. And the support from my close families and friends all around the world, they have really helped me to have confidence to continue what I do.
So everyone you met basically had like a little bit of like influence on you and on your career trajectory. There's not like one big mentor who like had an immense impact in your life.
Yeah, every moment of my life, there are certain figures who are more influential, but I also try not to burden someone for further, and their inspirations and support comes from the people who may not be the most outspoken, and I appreciate every support, loudly spoken, softly spoken, doesn't matter. I appreciate them all in
Yeah.
every front. And even this interview, when you asked for an interview, I was quite touched, and then it was also very encouraging that someone wants to hear my story more, and that's also quite supportive. So.
Well, so it was really a pleasure that you came to the podcast. Thank you so much for doing this.
Thank you very much.